Doctors Gardner and Wiseman, thank you so much for taking the time to share your expertise tonight. It's an exciting time to be an astrophysicist, right?
It certainly is. Dr. Gardner and I, John and I, are very glad to be here, and we're so excited about not only Hubble, but of course James Webb. So he'll be telling you more about Webb. I'll get started talking about Hubble, if that's okay.
Sounds great.
All right, so let me share my screen. We are astrophysicists at NASA's Goddard Space Flight Center in Greenbelt, Maryland. And Goddard is the NASA center that is basically the central center for these two missions, the Hubble Space Telescope and the James Webb Space Telescope. And so there's a lot of excitement right now going on. I'm going to tell you just a little bit about trying to cover the whole Hubble mission in 20 minutes is a challenge. But Hubble, as we know, has basically changed textbooks. It's changed what we know about everything from what's going on in our own solar system to other galaxies and the universe as a whole. And so you can find out lots more than I can tell you about today by perusing Hubble's website, which I'll show you the link later, but also we are active on social media at NASA Hubble. And you can, of course, contact me if you have other questions as well. Here's some of the stats on Hubble. So Hubble was launched back in 1990. So this year we've actually celebrated Hubble's 31st birthday of operations, and we're still going strong. It's in low Earth orbit. So it's orbiting the Earth at a height of about 340 miles, more or less. And that's very different from the Webb telescope's planned position in space, which Dr. Gardner will tell you about. Hubble's whizzing around the Earth about every 95 to 97 minutes in this low Earth orbit position. So it's moving very fast, but it has very good components to keep it stably pointed. So that's why we can point to distant objects, get very clear images, and transmit them down to the ground. And of course, the reason that it's up there is to get above the clouds. So Hubble isn't a lot closer to what we're observing than the ground, but it is above the atmosphere, and that gives us the sharper images. It's whizzing along at over 17,000 miles an hour. So by getting above Earth's turbulent atmosphere, we can get these very sharp images. And our atmosphere also filters out some kinds of light, like ultraviolet light, that we really want to receive from distant sources in space, because it teaches us things that we want to know. So by getting above our filtering atmosphere, we can see some of those wavelengths of light, and we can get very sharp images. So this is the core of a globular cluster of stars called Omega Centauri. If you were to look at a cluster of densely populated star regions like this from a telescope on the ground, it might be kind of blurred as the light kind of blends together from the different stars. But here you can differentiate star from star in this very crowded cluster and see that not all stars are the same, right? Stars are different brightnesses, they're different colors in their outer atmospheres, which represents different temperatures. If our own sun were in such a dense region and we could get far away from it to look back, it would look like one of the moderate sized or smaller sized stars that you see here, but we're not in such a dense cluster. And of course, Hubble has shown us tremendous beauty as well as activity in the heavens. So here's one of my favorite Hubble images. Of course, there are many like this, of a beautiful nebula of gas that is ionized, which basically lights it up into these beautiful colors. And it's lit up by stars that have recently formed in the core of this region. So you see this cluster of massive stars in the middle here, and they are bigger than our sun. And some of them are powerful enough to light up the surrounding gas, ionize it, and then that creates the glow and colors as those ionized atoms recombine. And we can also see that winds from these stars tend to eventually blow away this leftover gas out of which they formed. But in the intermediate time, we see these winds carving out these interesting structures and pillars and columns. All of this tells us that the universe is very active. It's beautiful, it's also active. Stars are still forming, stars are dying, And there's a lot of activity in between those 2 points as well. Here's an image we released this year for Hubble's 31st birthday. It's a single star, what we call a luminous blue variable star, that's had some hiccups, and one of those bursts or hiccups created this surrounding sphere of material many years ago. And so you can see the star and also the material around it, and some of the winds from the star are carving out structure in that surrounding material as well. So you can see the shell around the star, and that again tells us that stars themselves are not stagnant objects. They are active. We use Hubble in complementarity with other telescopes. So Hubble is an example of a space telescope. That's it up there at the top. But there are quite a few other telescopes in space as well already. And we work in coordination a lot of times, in scientific complementarity with telescopes that are on the ground as well. So here's some examples: the Keck telescopes on the lower left in Hawaii, and the array of radio telescopes that pick up radio millimeter and submillimeter wavelengths of radiation in South America. All of these have different niches of capabilities. Different telescopes can receive different kinds of light, or they see different fields of view. And in such a manner, we can learn something about planets or stars or galaxies by taking information from several different types of probes or telescopes, and then combining what we learn to give us a better understanding, a fuller understanding of what it is that we're trying to do. So Hubble certainly works in complement with other observatories already, and we certainly will with the upcoming Webb telescope, as we'll hear soon. I thought you might enjoy just seeing a little funny image. It wasn't always the case that the space telescopes were imagined to be functioning as they actually do today. Back in the 1960s, people were imagining that a space telescope would actually have the astronomer actually at the telescope in space. So I would love to do that. That would be really fun. So here's a diagram of an astronomer actually floating around inside a space telescope. Now it turns out that that's not necessary and not even practical, but it is funny to think about how different visions of space telescopes were considered before we actually came up with the working model for the Hubble telescope and subsequent space telescope. So Hubble was launched on Space Shuttle Discovery back in 1990. And the reason Hubble is so active and robust, we're at the peak of our scientific capabilities in return right now, even 31 years into the mission, is because we've had a series of astronaut servicing missions over the years. And these 5 returns to the Hubble telescope by astronauts on the space shuttle have enabled repairs and enhancements and extended the life of the mission. So here's a quick kind of graphic of the various missions over time, the launch and then subsequent servicing missions. That's what the SM stands for: servicing missions 1, 2, 3A, 3B, and 4. The last one we did was in 2009. It was a very comprehensive servicing mission, repairing some science instruments, putting in new science instruments as well, and new batteries, gyroscopes. So they left the telescope in wonderful shape. So even though the space shuttle is not operating anymore, so we can't do those kinds of classic servicing missions anymore for Hubble, we're really thankful that the observatory is in such terrific condition that combined with a really expert crew of engineers and technical oversight staff on the ground constantly paying attention to Hubble's technical health, we think Hubble will be providing wonderful science throughout this decade and even hopefully beyond. So Hubble's in good technical condition. It's at the peak of its scientific return even now. And it's a full observatory. It has a whole suite of different kinds of cameras and spectrographs that give us different kinds of information. And it's a general purpose observatory. So we do all different kinds of science with Hubble. We've used Hubble to understand things about our dynamic solar system, stars. Now we're even studying planets orbiting stars other than our sun. We call those exoplanets. They're outside our solar system. When Hubble was designed, we didn't even know of any planets outside our solar system. And now we know of thousands of them discovered by other observatories, and Hubble is doing follow-up observation. And then looking to other galaxies, even mysterious things like black holes within galaxies, and the universe as a whole, cosmology. So Hubble is used for many, many different types of astronomy and astrophysics. Let's look at some of it. So here's a beautiful, beautiful image of Jupiter. The advantage of Hubble being up decades is that we can go back over and over again to the solar system objects and see if they change over time. And indeed they do. We see active weather on Jupiter. We can combine our observations of planets with probes that actually go to these planets and moons and send back information, and they work in complement. So for example, we are studying Jupiter now with Hubble, looking at it from the vantage point of orbit around Earth, but we're also studying Jupiter with a probe called Juno that's actually right orbiting there in the Jupiter system, taking measurements of its magnetic field, gravitational field, and other environmental factors, and studying it with Gemini, another telescope that's on the ground on planet Earth. And these three facilities study different things. They reach at different depths into Jupiter's atmosphere and tell us different things about storms in that system. So that is a wonderful way of complementary work between telescopes on the ground, telescopes in space, and probes that actually go to these places in the solar system. Hubble actually can see different kinds of light. So we call it panchromatic capabilities. Hubble can see in ultraviolet light as well as the visible light that our eyes can see, and even somewhat into the infrared part of the spectrum of light. So here's a famous region people know of from Hubble, sometimes called the pillars of creation, M16. This is one of those regions being carved out by stars that have recently formed in visible light. But Hubble can tell us more about this image by looking in different wavelengths. So on the left is the classic image with a previous camera on Hubble of this region. The middle is the more recent image taken with the newest camera put on Hubble. It gives us a wider field of view and a sharper image. And then on the right is an infrared view of that same region using the infrared capability of Hubble's newest camera. And you can see through a lot of that veil of dust and gas. You see a lot more stars, and you can see into those pillars of dust a little bit, and you can see active hot regions in there, and especially on their tips where new stars are in the process of forming and heating up. So this different type of information, of observation, gives us different information that helps us understand more. And Hubble also sees the other type of light on the other side of the visible part of the spectrum, the ultraviolet. That's like super blue light, very energetic. So here we look at Jupiter again in visible light, but if we add on Hubble's view in ultraviolet light, we can actually see the bright emission from its aurora, the northern lights, if you will, on the poles of Jupiter. And so I think that's really cool to combine the visible image showing us the beautiful atmospheric bands of Jupiter with the ultraviolet light showing us the interaction of Jupiter's magnetic field with the solar wind. And that tells us something about how strong Jupiter's magnetic field is and how interactive our sun is with planets in the outer solar system. We're even using ultraviolet capabilities to study Jupiter's moon. So here's Europa, fascinating ice-covered moon. This image was made from the Galileo probe, but it's overlaid on a Hubble image of the silhouette in ultraviolet of this moon over the backdrop of Jupiter itself. And we can see these plumes of what we've determined as water vapor being ejected from cracks in the ice on Europa. So that tells us that the liquid ocean under the ice is actually able to eject some of its material. And we're excited about that for future studies of Europa. And we're studying very interesting, weird things coming through the solar system now that originated from other star systems. So that is really very cool. We recently observed and monitored this weird asteroid-like object coming through called Oumuamua, and then more recently Comet Borisov. Both of them have trajectories that seem to indicate they came from other star systems, were ejected, are passing through our solar system. Other telescopes were used to detect them, but Hubble's been used to follow up on observations. We are looking at exoplanet atmospheres with Hubble. Hubble was the pioneer at studying the composition of some of these exoplanet atmospheres. And we're using Hubble now to find out even more about these many detected exoplanets. We found water vapor. And of course, the goal is in the future to find out how many of these star systems have planets that are similar to those in our own solar system. So Hubble is a pioneer in that kind of work. And we're looking outside our galaxy to other galaxies as well. So here's an example of a beautiful spiral galaxy that Hubble has seen. If you look carefully, you'll see other spirals and other types of galaxies in the background. Hubble has shown us that galaxies are not stagnant, that throughout cosmic history, galaxies have gone through collisions, and that would include our own Milky Way. And these mergers have built up galaxies into bigger structures, more massive. Merging seems to be a common part of the history of our universe. And of course, my favorite and one of the most famous images from Hubble is the deep field. Hubble has done quite a few deep fields now, but these are integrations of time using Hubble to collect faint light in a small field of view over a long time so that the faintest objects show up in the image. This particular field shows us thousands of smudges of light. These are not stars. These are, for the most part, galaxies outside our own galaxy. So these are galaxies in their own right, and many of them with hundreds of billions of stars. And if you imagine this extrapolated over the whole sky, this is the kind of amazing, rich universe that we live in. It's mind-boggling to me every time I look at this. If we could get far enough from our own Milky Way and look back, we would see this kind of thing, and our galaxy would look like one of those spirals that you can see kind of in the upper left part of this image. Now, of course, these galaxies are not all at the same distance. Some of them are closer and some of them are farther away. So if you kind of pull them out and determine their distances, which is not trivial, but astronomers spend a lot of time trying to understand how to determine distances, you can line them up. And here you see the more nearby galaxies have been put in the circles on the left here, and the more distant ones on the right. And you see they look different. We're looking back in time because it's taken more time for the light to get to us from the more distant galaxies on the right than the ones on the left. So the ones on the right are earlier in their stages of forming and growing, and they haven't merged as much. They haven't had time to grow and to take on the more what we call mature structures as the ones on the left. I think Hubble opened our eyes to this understanding that galaxies change over time, over the billions of years of cosmic history. We also now understand that there's a lot of unseen material. So dark matter fills galaxies and also fills clusters of galaxies. So here's a cluster of bright galaxies, but what we don't see is that most of the matter that's unseen is strong enough. There's enough matter to actually warp space-time enough that it distorts the light from background galaxies behind this cluster. So you see these kind of weird streaks and arcs of light. That's because the dark matter in the foreground cluster is magnifying the material from behind and distorting it. And so that helps us understand something about dark matter in the foreground cluster. And it also helps us understand things about very distant galaxies that get magnified by this effect that's called gravitational lensing. Here's one of those very distant galaxies that Hubble has picked up. It doesn't look very pretty, but it is blown up here so you can see. This is a galaxy shining from within the first few 100 million years of the beginning of the universe. And so we can see, we think the universe is about 13.8 billion years old. Well, we're seeing to within that first 0.8 of the 13.8 billion year history of the universe. And Hubble is able to pick out some galaxies within the first few 100 million years of the beginning of our universe. The Webb telescope, as I'm sure John will talk about, will see even deeper into space and time. So Hubble's made well over a million observations, and out of that have come well over 18,000 scientific publications. Hubble's achievements include verifying the existence of black holes in the cores of galaxies, establishing a better understanding of the expansion rate of the universe, and we're still working on refining that. And even along with ground-based telescopes has verified that our universe is in fact accelerating due to something mysterious called dark energy. We did the first measurement of the chemical composition of exoplanets, and we've been studying how stars form. So let me, in the last minute here, just point out that we have things to do with Hubble. Not only did a Nobel Prize come from that discovery of dark energy, but we're using Hubble going forward to understand more about how dark energy has impacted the history of the universe, how dark matter is impacting the universe, closer to home, looking for the characteristics of exoplanets, still finding surprising things about our own solar system, and even studying sources of things that don't radiate like electromagnetically, but gravitational wave sources. So we have a lot of interesting things to do with Hubble. And as I said, as we look out in the universe, as this graphic displays, as telescopes got better over time from top to bottom here, the sensitivity is allowing us to see farther, deeper into space by seeing fainter objects. That's like looking back in time, which is what that bottom axis is telling us, the time from the beginning of the universe as we understand it on the right-hand side. The Webb telescope will be able to see even deeper to more infant galaxies that are forming even closer to the beginning of the universe as we understand it. There's the Webb itself, the mirror at Goddard Space Flight Center, and I'm sure John will have some pictures of this. It's a wonderful facility. It will complement Hubble. Here's a quick graphic that shows you the Hubble telescope and its mirror on the left, the Webb telescope and its mirror, its segmented mirror on the right. Webb has a bigger mirror. It'll be very sensitive, as John will explain, and they see on the bottom a different color range. So you can see the colors of the rainbow there on the top little band there, and then you see that Hubble sees visible light into the ultraviolet on the left and a little bit into the infrared. The Webb telescope sees red light all the way much deeper into the infrared. So these observatories will complement each other. And I'll just mention quickly that there's a third space telescope that's being designed and developed right now called the Roman Space Telescope, and it will complement Webb and Hubble. It will launch a few years down the line from now, but it will have a much bigger field of view. It will be an infrared-based observatory, but as you can see in this picture here of Andromeda, part of the Andromeda galaxy, the Roman footprint of what it can see is a much wider field of view to do surveys and things that will complement what Webb and Hubble can see, and you can see their little footprints there below the Roman footprint. So with Hubble continuing to inspire us, I'm looking forward to the years to come. Here's an image of a student looking at an image that's been enhanced for visually impaired people to be able to feel the difference between, in a way, between galaxies and stars and planets. And be inspired by it. The upper right is from a church near Johnson Space Center that has used all the windows of the church based on Hubble images to inspire people. And even U-Haul trucks are inspiring people with Hubble. So the Hubble mission, we believe, will continue with strong capability, likely through the 2020s and hopefully beyond. And its scientific capabilities are going to complement future missions like the James Webb Space Telescope to launch later this year and the future Roman Space Telescope. So take a quick screenshot of this if you want more information. That's our website. And with that, I will pass it along to our next speaker. Happy 31st birthday, Hubble.
Okay, thank you, Jennifer, for a wonderful setup for my talk. Just as Hubble is a wonderful setup for the James Webb Space Telescope. Let me start sharing my screen. Okay, so the James Webb Space Telescope is a large, cold telescope in space. It is the successor to the Hubble Space Telescope, and I want to start off by agreeing with Jennifer. It's not a replacement. Nobody's going to, everybody, all of the astronomers want to use the two telescopes together, just as Jennifer and I would like to use the two telescopes together. So it's a successor, which means that the design of Webb was based on what we learned from the universe, about the universe, by using the Hubble Space Telescope, and thinking about how can we take that a little bit further and learn even more. So back about maybe 5 or 6 years after Hubble was launched in 1990, groups of astronomers got together and started thinking about what we wanted as a successor. And what were the big important questions that Hubble was bringing up that we would want to answer? And what they settled on was the origins and evolution of galaxies, of stars, and of planets. Now, when you think about origins, that's the beginning. And beginnings are very important because they set the stage for the future development. But because stars, galaxies, and indeed children are complex systems, you also need to study changes over time, and that's what scientists call evolution. So when we worked on defining the science goals for the successor to Hubble, that's called the James Webb Space Telescope, we decided that we would look for the first galaxies to form in the early universe after the Big Bang. We would look at how galaxies change over time, or galaxy evolution. Within our own galaxy, the Milky Way galaxy, we would look at the formation of stars and planets. And then finally, we would look at planets, both extrasolar planets or exoplanets and planets in our own solar system, and look at what might be the conditions for life on other planets. So Jennifer showed you this picture, the Hubble Ultra Deep Field. I also love this picture. It is the faintest picture that humanity has ever taken. And in this picture, as Jennifer said, everything you see is a galaxy. Now, when astronomers look at this picture, they see the nearby galaxies at which they can study in detail, but they also zoom in on some of the very faintest and the reddest galaxies that are in this picture, because those are the galaxies that are the furthest away. And as Jennifer mentioned, we can look backwards in time by looking at things that are very far away, because they're so far away that the time it took for the light to travel at the speed of light, the fastest speed there is, the time it took for that light to travel from those galaxies to our telescope, to Hubble, is most of the age of the universe. It's looking backwards in time, backwards 13 billion years to when the universe was less than 1 billion years old. And when we find the galaxies that Hubble detected in this picture, the most distant galaxies we can see, some of those galaxies were actually already several 100 million years old at a time that that is the furthest back we can see with Hubble. So in order to go even further back to when these galaxies were first forming, we needed a telescope that's bigger than Hubble so we can see fainter things. And then also because as the light travels through the expanding universe, it stretches out the wavelengths so that blue light becomes red light, becomes infrared light. And so we had to move off further into the infrared than Hubble can see in order to see back to the first galaxies that formed in the universe. So that drove the design of the telescope. We need something bigger than Hubble, and we need something that can see in the infrared. And since infrared is heat, we need to have a very cold telescope. Now it turns out, and Jennifer showed this picture as well, it turns out that although we initially decided to make an infrared telescope to see distant galaxies, infrared is also very good at looking into the dust clouds where stars form. So as we look at this, look at the Eagle Nebula in the infrared, we can see through to the places where the stars are forming in the dust clouds. And then last but not least, the study of planets, and this is a exoplanet system with 7 known planets, and each of these planets is transiting across the face of the star, its own star. And when it does that, the light from the star goes through the atmosphere of the planet, and we can then learn about the atmospheres of these planets by studying the light that has traveled through from the star, through the atmosphere of the planet, into our telescope, and we can analyze the constituents of the atmosphere. And Webb will be looking for things like planets that have liquid water on their surface or beachfront property, which is liquid water is one of the necessities of the kind of life that we have here on Earth. And then finally, within our own solar system, because of where it is, and I'll show you that in a minute, Webb cannot look at Mercury or Venus or the Earth or Moon, but it can look out at Mars, Jupiter, and Saturn, which are very, very bright. And if you build a giant telescope and put it in space, the planets are kind of too bright for it to look at with some of the camera modes. But we have ways of studying Mars, Jupiter, and Saturn. And then Webb will be very good at studying the outer solar system, Uranus, Neptune, Pluto, other objects out in the Kuiper Belt, moons of the outer solar system, and asteroids and comets. So let's do a quick comparison of Hubble to Webb. So first of all, temperature. Hubble is kept at room temperature as it goes around the Earth, goes in and out of the sunshine, and we use heaters to maintain a constant room temperature. And there's a picture of an astronaut up there with Hubble, and when the astronauts went up there, we did not want them to freeze. So Hubble is a room temperature telescope. But in order to see into the infrared, Webb needs to be a very cold telescope. And so it will hide behind this tennis court-sized 5-layer sun shield so that it can cool to 225 degrees below 0 Celsius, which is just 50 degrees above absolute zero. We have a different orbit. Hubble is in orbit 375 miles above the surface of the Earth, whereas Webb will be launching on a European rocket, the Ariane 5 rocket, on December 18th of this year, and will be going 1 million miles away from the Earth. That's 4 times the distance of the Moon. Now it's going that far away into a very special place in the solar system called the second Lagrange point. And at the second Lagrange point, the Earth and the Sun always stay lined up. As the Earth goes around the Sun once per year, the second Lagrange point goes around the Earth once per year, exactly the same amount of time. And so the Sun, the Earth, and the telescope stay lined up, and this tennis court-sized 5-layer sun shield can protect the telescope both from sunlight so that it can cool, and also from light from the Earth, the sunlight bouncing off the Earth and going to the telescope. And then finally, the difference in size. Hubble has a 2.4 meter mirror to collecting area, and Webb has a 6.6 meter primary mirror. But that brings up a question, because I told you it was launching on an Ariane 5 rocket, and the Ariane 5 rocket is only 5 meters in diameter. So how do you fit a 6.5-meter mirror into a 5-meter rocket? Well, the answer is that you have to fold it up, and then once it's out in space, it will unfold through a series of deployments. So this is an animation that the engineers have made about the deployments that happen on Webb. The first thing to come out is the solar panels that provide power, and then there's the communication antenna, and then we start unfolding the 5-layer tennis court-sized sun shield. There are protective coverings. Right here you see the mirror is separating from the spacecraft so that we can unfold the sun shield. There's protective coverings that fold back, and then we start pulling out the structure that holds the sun shield, and then the sun shield membranes themselves get pulled out and separated. Each of these 5 layers is separated by about a foot. They're about a foot apart, and because this is in space, there's vacuum in between those 5 layers, and it works like a vacuum flask to allow the telescope to cool. The final deployments are the 2 side wings of the primary mirror and the secondary mirror out on its 3-legged spider structure. And there you see Webb out in space pointing at distant galaxies. So now I'm going to transition and tell you how we build space telescopes. It's a very iterative process. We start with a small component, such as what's called a microshutter array inside one of our cameras, inside the spectrograph. We build a small component like this, we put it together, and we test it. So we will test it by putting it in vacuum and operating it at the temperature of deep space. And we'll also put it on a vibration table and shake it in the way that will happen during the launch on top of a giant rocket. And then we also blast it with noise, as will happen during the launch. And then we test it again to make sure that it's going to work, either with a cryogenic vacuum or thermal vacuum test or a deployment test. So having gone through the simulated launch and shown that the component works, we then assemble it into the next higher level, put the detectors or put the microshutter array into the instrument, and we test that. And we go through the same process. We then put the instrument into the instrument compartment and test that again. Then we attach the instruments to the telescope and we test it again. And this is the primary reason why, first of all, it takes a really long time to build a space telescope. And second, we're pretty sure it's all going to work because we have tested it so much. So I'm now going to show you some pictures of some of the equipment on Webb. This is the family portrait of our 4 cameras. We have a near-infrared camera, a near-infrared spectrograph, a guidance camera, and a mid-infrared instrument. And Jennifer said that Hubble can go a little bit into the near-infrared. Even our near-infrared camera can go a bit more into the infrared, and then the mid-infrared instrument is a capability that Hubble does not have at all, to look at longer wavelengths, redder light. So this is a time-lapse video of putting the mirror together, the primary mirror. The primary mirror on Webb is made up of 18 hexagonal mirror segments arranged in a 2-layer hexagon. And this is the assembly of those 18 mirrors onto the support structure backplane. Now, when we were putting it together, they had protective black coverings on top of the mirror to keep them safe. But once the mirror was fully assembled, and here we see just as the last one's going on, once the mirror was fully assembled, we took the protective covers off, and you could see that the mirror Webb's mirror is coated in gold. We used gold because gold is very highly reflective in the infrared. This is the secondary mirror, which is also coated in gold. And then here is the mirror, the Webb primary mirror, with a picture taken in the clean room. And the really interesting thing about this picture is that the photographer lined it up so that the NASA logo on the wall was reflected in the Webb mirror. And the fact that it's not, doesn't look like the logo looks like directly on the wall comes from the fact that this is a focusing telescope. It's not a flat mirror. It is a mirror that focuses the light. And there are the technicians who worked in the clean room wearing their bunny suits and wearing masks before wearing masks was cool, in order to protect the telescope from dust and any contaminants as they work on it. Now, this picture is the coolest selfie I will ever take in my life. Picture of myself reflected in the Webb telescope primary mirror. The next thing as we were assembling the telescope together is to install the instruments onto the back of the telescope. And I'll show you a time-lapse video of that installation. You can see up in the upper right the viewing window. And I was fortunate enough to get into the viewing window just about this point where I was able to watch the instruments be installed onto the back of the telescope. So having done that, put the instruments and telescopes together, we took that instrument package down to the Johnson Space Center near Houston, Texas, and put the telescope and the cameras into a gigantic vacuum chamber. This vacuum chamber is 12 meters diameter and 35 meters high, and was actually built for the Apollo program for the astronauts to practice walking in their spacesuits in a vacuum. So the Webb project took out the simulated lunar surface and installed a liquid helium shroud inside to get down to the operating temperature of Webb, and put the telescope and the cameras through a 1 month, actually it was a 3-month test, 1 month to cool down, 1 month of testing, and another month to warm it back up very slowly to room temperature when we could open the vacuum chamber. And there was a certain amount of personal heroics during this test because this was the time when Hurricane Harvey dumped 51 inches of rain on the Houston area. And the NASA workers at the Johnson Space Center, despite being in the middle of a hurricane, managed to keep all of the Webb hardware safe and kept the vacuum chamber running during that time. Meanwhile, we were building the spacecraft and the sun shield. This is a picture taken at the Northrop Grumman facility in Los Angeles. And that spacecraft and sun shield on their own were also put through a vacuum test. And the final thing, the final piece of assembly was to attach the telescope to the spacecraft. And so here is a time-lapse video of that installation, again, in a large clean room with a lot of masked people. And the installation of the telescope onto the spacecraft, which holds the partially deployed sun shield. And then the two are attached together. And then there was a test of the deployment of the sun shield. It had to be done on these tables because of it was being tested in gravity, whereas the actual deployment will take place without gravity. So there's the camera zooming around, showing the sun shield and the telescope. And finally just a still picture of the observatory. A couple of other beauty shots of Webb in the clean room. And this is a very recent picture taken with the observatory all folded up. All of the deployments have been put back, and we are almost ready to ship to the launch site. That will be happening in a few weeks or so, and the launch will be from Kourou in French Guiana in South America. As I said, it's a European launch on an Ariane 5 rocket. There's a couple of months down in Kourou, and then the launch will take place on December 18th. Shipping to the launch site will be done by boat. We have, we've been taking Webb around the country, around this country, by truck or by cargo airplane. But once everything is completely put together, it actually is too big to fit on the cargo airplane. And so it's going to go through the Panama Canal on a boat for the launch. I actually already showed you this launch video, so I'll skip that. And after launch, we'll need 6 months to turn everything on. The first month will be the video that I showed you of all of the major deployments. And then the telescope needs to cool to its operating temperature. And then we have to spend 3 months very meticulously lining up the 18 individual mirrors. When we first point the telescope at a star, we will see 18 separate pictures of that star, images of that star. And we need to line them up and go through a very complex process of converting 18 different mirrors into a single fully phased up optical surface. Then an additional 2 months to check out everything in the instruments, and 6 months after launch. So that would be next May, we'll have the first scientific images. So this, as I said, this has been a real long process. This is a picture of a model of the Webb telescope in 2005. And this is me down here looking 15 years younger, and only about 1/10 of the total number of people who are working on the Webb telescope, because it's a huge undertaking. And then here is, just last year, here is the final assembled and deployed Webb with some of the technicians that worked on it at the Northrop Grumman facility. So I'd like to thank you for attending, and I believe at this point, Jennifer is going to turn her camera back on, and we will both work on answering some questions. So let me just stop sharing.
Yeah, thank you both. Boy, it's interesting stuff. I enjoyed hearing about it. I know everyone else did as well. And just real quick, a reminder for everyone, if you have a question, you'll see a Q&A chat box at the bottom of your screen. Type it in there. If you're on Facebook, you see me looking off to the side here. I'm monitoring Facebook as well. So just type your question in the comment section. We'll start with this one. Dr. Wiseman, the question is, will the rise of commercial spaceflight offer the opportunity to send up more astronauts to do repairs on Hubble, now that the shuttle, of course, is no longer in use?
Sure. So that's certainly a hot topic of conversation. Right now, we at NASA don't have any plans to service Hubble in the future, because Hubble's working very well, and we anticipate, even with operations and commanding we can do from the ground, that we can keep Hubble very scientifically productive. But that hasn't stopped people speculating about whether there are other types of vehicles other than the space shuttle that could be used to service Hubble. And so, nothing's out of the question. There are certainly companies that are thinking about it. It's complicated because you have to have a spacecraft that can dock with Hubble in low Earth orbit and support these extravehicular activities of astronauts going out in spacesuits, out of the spacecraft, doing the kind of repair work not near the space station or anything like that, sometimes for days on end. And so far that no one has that distinct capability of docking with Hubble and doing the kinds of servicing we've become accustomed to. But it isn't out of the question to try to think of those kinds of possibilities. So I'll just leave it at that.
And Dr. Gardner, we have a few questions related to this. Since the James Webb will be so far away, if there's any kind of problem, there's really no way to make it repair, correct?
That's correct, and that's why I told you how we build space telescopes with lots and lots and lots of testing. It's actually true that Hubble was designed to be serviced or designed to be repaired from the very beginning. To some extent, Hubble and the space shuttle grew up together. Space shuttle was designed to launch and service Hubble, and Hubble was designed to fit inside the space shuttle. But that's not actually the normal way that NASA does satellites. Most satellites are like Webb, very thoroughly tested on the ground and then sent off, and most of them work without repair. So Webb will be a very long ways away. 1,000,000 miles is 4 times as far as we ever sent astronauts, and that was the astronauts that went to the moon, and we haven't had astronauts that have gone that far recently. So from the beginning, Webb was designed to not be serviced, and part of the difference is also that Hubble is built in a very modular fashion. The instruments can be just pulled out. You unbolt a couple of bolts and you pull out the camera and you put in a new camera. Whereas with Webb, in order to fit this very large mirror, very complex instruments, along with the sun shield, packed very tightly into the rocket, we made it very integrated. And so it's really a whole lot of effort to pull it apart and do any repairs. So that was part of the trade-offs that were made when we first decided to build Webb, send it so far away. It was not built to be serviced. But as Jennifer says, you never know what clever people can do. Webb's got a design lifetime of 10 years, and we hope that it'll last a whole lot longer than that. And if it does, that puts us into the 2030s, and the capabilities that we end up having in the 2030s might be more capable than what we have now, and maybe people could start thinking about what to do as we get towards the end of Webb's lifetime.
It might be routine in the 2030s to travel 1,000,000 miles away.
We'll see.
We've got an interesting question. Someone asked, are these solely NASA projects, or are they a collaboration of many nations?
So I'll just jump in quickly. So certainly for Hubble, it's a collaboration between NASA and ESA. The European Space Agency is still a major partner in our mission. And the Canadian Space Agency has also been a partner, especially they're known for the robotic arm that we've been using for servicing a Hubble on the space shuttle. And we have astronomers from around the world who use the Hubble Space Telescope to do science. So certainly, while NASA is the major lead and partner in the mission, we're not the only participant. And I'll let John answer for JWST.
Yeah, for Webb, it's the same thing. It's a partnership between NASA, the European Space Agency, and the Canadian Space Agency. In all, there are 14 countries that are contributing hardware to the Webb telescope. I did mention that the launch vehicle will be provided by the European Space Agency and Ariane rocket. ESA is also providing sort of 1.5 of the 4 cameras, and the Canadians are providing 1 of the 4 cameras. So they're certainly major partners. And as Jennifer said is true for Hubble, the selection of the science programs that are done is through a peer-reviewed competition. Astronomers from around the world write their proposals, and a team of astronomers puts a lot of effort into reading those proposals and choosing the very best ones to do with both Hubble and with Webb. And it's a very competitive process, and it's the way that we ensure that both of these telescopes will be doing the most compelling scientific questions through this competitive process. And it's done every year, so we also stay right up to date.
All right, this is a question for the Webb. It's sort of related to the Hubble as well. How will cosmic rays or maybe solar flares or anything out in space, how will that affect the James Webb? And I guess, Dr. Wiseman, have things affected the Hubble being out in space?
Yeah, so I'll start. That is part of the space environment that we design for. There are several things that can happen as the particles go through the detectors in the camera. They can very, very frequently will sort of temporarily knock out one of the pixels of the camera. So normally what we do, both with Hubble and we'll do it with Webb, is we take a picture and then we offset just a little tiny bit. It's called dithering. We offset a little bit and we take another picture and do that multiple times. And the kind of holes that are in the data we can fill in from the other pictures. So that's a routine part of using a space telescope. Is we will take multiple exposures and we'll download them to the computers on the Earth, and we'll add them together. So all of the pictures that both Jennifer and I showed you were done through this process of taking multiple exposures. The particles also will go through the electronics, and much less frequently, but very occasionally, it will require a reset of the electronics. Again, all of the electronics we put into space telescopes are what's called radiation hardened. It does cost a bit more than just buying cameras off the shelf on that work on the Earth, but it's part of what we do. It's built into the process, and we just plan for it.
Yeah, so I don't have much to add to that, but we certainly have to accommodate for the effects of particles, cosmic rays, things hitting the observatory and our instruments. We also have to accommodate for the fact that sometimes we get hit by actual little particles of, debris in low Earth orbit, and you can see that when when one of the cameras was brought back in the last servicing mission from Hubble, it had an outward facing side that got hit by some of this little space debris, and you could see the little pock marks about it. So that's another type of impact that we face. But we know how to deal with much of these issues, and that's why you don't hear about it too much, because we're able to do great science even though we understand the degradation that's caused by some of these cosmic ray particles and other impacts.
Yeah, I'll also add that one of the reasons why Webb has a 5-layer sun shield instead of a single layer is that if a micrometeorite went through the sun shield, it would be very unlikely to have the sun perfectly line up through 5 holes and hit the primary mirror. Whereas if there were if there were just one layer, that would be a much bigger effect.
All right, we have a comment from Chris who writes, thank you so much. Wonderfully presented and exciting to see the progress and future. And I'll have to second that. We're a little past the top of the hour, so let's wrap it up with one more question. Dr. Gardner, you mentioned that there's a selection process for both, what to observe for the Hubble and of course for the James Webb Space Telescope. Do you know already what you're going to be looking at first with the James Webb? Has that decision been made?
Yes, well, sort of. So the very, very first pictures that will be right immediately at the end of the 6-month commissioning and will be taken and presented at a press release that say, hey, we're starting. Those have not yet been selected. But what we have done is we went through a competitive process and chose 13 different scientific programs, all of which will take place within the first 3 months. And these 13 programs, called the Director's Discretionary Early Release Science Program, so DDERS, those programs were all chosen to kind of demonstrate the scientific capabilities of Webb, and also to provide data for future proposals. We'll have to, not too long after we start getting data with Webb, we're going to have to start the competition for what we're going to do in the second year. And so these 13 early release science programs were designed to put some pictures and other data in the hands of astronomers so they can kind of play with it and see what the capabilities are, so that they can then plan the second year proposals. So if you want to see the details of those, you can Google James Webb DDERS, and you'll come up with the abstracts of the 13 proposals. But they range from all the way from pictures of Jupiter to the very distant universe, and kind of, picking and choosing the good stuff in between. So it'll be an exciting ride.
If I could just add a little to that, we have a very competitive process already for Hubble Space Telescope proposals. As I mentioned, scientists from around the world every year put in proposals, and then there's an expert review to choose the best ones. And some of those proposals are what we call James Webb Space Telescope preparatory science. So they're observations that are designed to be done with the Hubble Space Telescope, but that will help us learn something that will prepare us to make better use of the Webb Space Telescope. So we're already doing that preparatory type of science with Hubble that will help us get the best use out of the James Webb and help us to use that information in a complementary fashion. And we're also going to be executing proposals, doing proposals that are designed to when both Hubble and Webb are operating, to use both of those telescope capabilities somewhat at the same time or in the same time frame. So we can use the different wavelength and the different capabilities of these two observatories in a complementary fashion. So we're going to be learning a whole lot more about the universe when Webb is operating, and in this complementary fashion than we've ever known before. And so we're very excited about this, and the coming decade should be really exciting for astronomy.
Yeah, the two telescopes will work together perfectly.
Yeah.
And I can't wait to see what you guys come up with. Here at the Linda Hall Library, we have a cosmology theater, which most of the time we show view space, a feed from the Space Telescope Institute. So we love seeing the Hubble images, and we can't wait to see more of those, plus the James Webb images that'll be coming here soon. So thank you, Dr. Wiseman. Thank you, Dr. Gardner. A wonderful presentation. We're getting several comments from people too, saying how much they enjoyed the presentation. Someone wrote, I hope to hear you both talk again. And I was going to say that too. We'll have to do this again and hopefully do it in person here at the library.
Well, you're very welcome. John and I have enjoyed doing this, I'm sure. And I just want to say that a lot of you put in questions that we didn't have time to get to, but I've been able to see them all. They're really good questions. So thank you for sending them in. They're very thoughtful and good questions.
Yes, and thank you for inviting me back. I was at the Linda Hall Library in 2009. I really enjoyed my visit then. It's too bad we couldn't come to Kansas to do this in person, but you know, maybe in a future year when things get back to normal, Jennifer and I can come in person. But
I hope so. I hope it's
certainly
sooner
enjoyed
rather
doing
than
it
later.
virtually.
And thank you everyone for attending tonight's program. For more information about upcoming Linda Hall Library events, follow us on our social media platforms and visit our website at lindahall.org, where I also encourage you to sign up for our e-newsletter. That's the best way to stay up to date with our upcoming programs. When visiting our website, I hope that you also take the opportunity to support the Linda Hall Library Foundation. Your contributions help make all of our programs possible and freely available. So thank you again, everyone, and have a great rest of your evening.